Okay, let's start. Sorry for the delay, and we are very pleased to have Alex Pieloch from Columbia University, and he's going to tell us about sections and unirulings of families over P1.
Yeah, great. Thanks for having me. And sorry about all the technical stuff. Sorry that I'm going to be talking.
It's our fault, so don't worry about it.
Right in your face as well, Julian. Okay, so today I want to talk about an application of symplectic topology to algebraic geometry. So let me go ahead and fix some notation. So we're going to let pi from m bar to p1 be a morphism of smooth projective varieties over C. Okay, so we have some total space, m bar. This is some complex Kähler manifold, and it's sitting inside of CPN for some very large n. And by morphism, I'm going to mean a holomorphic map that's non-constant. Okay, so away from a finite number of singular values, we just have some smoothly varying family of complex Kähler manifolds. And then for some singular points, these degenerate into slightly more complicated singular subschemes. Okay, so here I've drawn a picture where the fiber is kind of one-dimensional, but really the fiber can be any arbitrary dimension that you want. Okay, so the result that I want to talk to you about is a sort of constraint on the actual complex geometry of these families when they have very few singular fibers. So there's two parts to this theorem. So the first states that if one of these families has at most one singular fiber, so either the morphism is completely smooth or there's a singular fiber over infinity, then this total space M bar is uniruled. That is, through every single point in the space, we can find a non-constant rational curve passing through it. And moreover, this map also admits an algebraic section. Okay, so now if we move up one more and we allow for two singular fibers, then I need to impose one additional constraint. So for the rest of this talk, let's just assume that when we have two singular fibers, we have 1 over 0 and 1 over infinity. And we're going to remove the fiber over infinity. So now this is some space that's fibering over C with some singular fiber at 0. So if the first Chern class of that space over C vanishes, then we get a very similar conclusion. So again, we get this total space is uniruled. And now, instead of getting sections, we get rational multi-sections. Okay, so before I talk about any motivation for this, let me just make a couple of dumb remarks about the theorem itself. So the first thing that you should notice is that statement 1 is about sections and statement 2 is about multi-sections. And so in general, this is just sharp. So the existence of multi-sections cannot in general be improved to existence of sections as soon as you have two singular fibers. And so the counterexample is rather dumb. So take your total space to be P1 and take any degree K map where K is greater than 1 from P1 to P1. Okay, so in this case, just by dumb degree reasons, there are no actual sections, only multi-sections. Okay, so here we have K points away from 0 and infinity. And as we move into the poles, they all collide into a single point. Okay, so this is the first remark. The second remark is that the projectivity assumption of these families is actually necessary to get these unirulings and sections as well. And so the counterexample is just the Hopf surface. So diffeomorphically, this is just S1 times S3. And we get some holomorphic map from the Hopf surface to P1 that's given by projecting out the S1 factor and then applying the usual Hopf map on the copy of S3. Okay, so you give this to some algebraic topology student, and they tell you that pi2 of this total space vanishes. And so just for dumb degree reasons, we can't actually have a map of a section into this total space M bar. If we did, then its degree would be non-zero. Okay, so this projectivity assumption is necessary. The final remark is that this theorem fails as soon as we allow for more than two singular fibers. So 2 or less is the optimal bound. And again, the counterexample is fairly simple. So you just take some branched cover over P1 such that the Euler characteristic is negative, right? So you either have a torus or some number of donut holes. So clearly it's not going to be uniruled and it's not going to admit any particular rational curves. So no sections or multi-sections. Okay. So those are just some simple remarks. So now let me actually talk about the motivation for why you should suspect that such a theorem would be true. So the motivation for this result comes from Hodge theory. So for this discussion, let's just go ahead and let pi be arbitrary. by which I mean it can have 77 singular fibers, 0 singular fibers, 102, whatever number you'd like. And we're going to fix an auxiliary space. So what we're going to do is we're going to take P1, and we're going to remove all of the critical values of this map pi, and then we're going to take the universal cover of that space. Okay, so let's just do a dumb sanity check. If we have 2 singular fibers, we get C star, so the universal cover is C. Okay, so in general, if we have 2 or less singular fibers, our universal cover is either going to be C or it's going to be P1. So in particular, it's non-negatively curved. So as an application of Griffith's work on period domains, you get the following additional structure coming from these smoothly varying families of complex scalar manifolds. So you obtain a holomorphic map that goes from this universal cover S to a moduli space. So this moduli space here, D, is the moduli space of polarized Hodge structures associated with fiber. So the fiber, being a complex scalar manifold, equips its cohomology with some additional structure. So all this map is doing is it's looking at your point in P1, it's looking at the fiber over that point, and it associates to that point in P1, or rather the universal cover, its associated polarized Hodge structure. So this is just encoding how the Hodge structures are varying as you move around inside of the smooth locus of this family. Okay, so using a distance minimizing principle, Griffith shows that if the Euler characteristic of this universal cover is positive, then this holomorphic map phi is actually constant. Okay, so if we kind of reinterpret this, this says that when our base is non-negatively curved, the variations of Hodge structures of these families are trivial. Okay, so there's nothing interesting that we are seeing from the viewpoint of the Hodge theory of these families. For all intents and purposes, they just kind of behave like the trivial families with respect to Hodge theory. Okay, so let me just kind of orient people for that maybe aren't super comfortable with Hodge theory. So what is this in the case where the fiber is one-dimensional? So we take some genus G curve. So in this case, Griffith's map is the map that takes the fiber, a curve, to its associated period matrix inside of the Siegel upper half space. Okay, so the Siegel upper half space is actually just hyperbolic. So it has negative holomorphic sectional curvature. And so in particular, if you have any holomorphic map that goes from a non-negatively curved curve into this hyperbolic manifold, then it a priori has to be constant. Okay, so this is the proof of Griffith's result in this particular case where the fiber is a curve. And so the natural question that always arises when you see some type of Hodge theoretic triviality is whether or not it is the shadow of some type of algebraic cycles or actual complex geometric features of the associated space, right? Hodge theory is some statement about homological algebra, but what we really care about is some statement about geometry. And so this is one way that you can interpret the statement of this theorem. Okay, so the algebraic cycles that we are producing are namely these algebraic sections or multi-sections. And the complex geometric features that we are detecting is the fact that these families have to be uniruled to be fibered over P1 in this particular manner. Okay, so this is a symplectic geometry seminar. So you should kind of ask the obvious question, why does a symplectic geometer think they have anything to say about this particular question? So there is some motivation from symplectic geometry. So if you have a map from M bar to P1 that has no singular fibers, so it's completely smooth, then actually you can conclude that pi emits a section. And so the proof of this follows from the Seidel representation, or really some of the geometric instructions that go into constructing the Seidel representation and some of its algebraic properties. So Seidel constructs the Seidel representation under some sort of condition between C1 and the symplectic form, and Macduff uses some virtual techniques to construct the Seidel representation and its properties in more generality. Okay, so even though Seidel and Macduff's proof and my proof for this particular overlapping case both go through the symplectic category, they're nevertheless very different symplectogeometric constructions. Okay, so Seidel and Macduff use sort of a symplectic connect-sum construction to go about getting these particular sections. So in my particular case, I'm going to instead use a flavor of Floer theory that is quantitative. So I'm going to use something called local symplectic cohomology, which is going to be a cohomology group associated to symplectic manifolds that we will use to actually detect the existence of these rational curves inside of our space. Okay, so maybe I will give now the very, very high level idea of what the proof is before I go into any of the gory details. So as I mentioned, we use this invariant called local symplectic cohomology. So the idea of local symplectic cohomology is that for every single compact subset of a convex symplectic domain, we're going to associate a chain complex. So we construct the generators of this chain complex from the Hamiltonian dynamics near our compact subset. So we're going to have some Hamiltonians. We're going to look at the one periodic orbits of the Hamiltonians. And we're going to have some algebraic way of just focusing in on the Hamiltonians, or sorry, the orbits that are nearby our compact subset and ignoring the ones that are very far away. Okay, so this will give us our generators. And then as usual in Floer theory, we are going to construct our differentials by counting pseudo-homomorphic curves, Floer trajectories inside of the total space. Okay, so what we're going to do is we're going to apply this setup to our particular situation. So we're going to take M bar and we're going to remove a singular fiber. So we have this space M, and we're going to look at the inverse image of a disk of finite radius. So this is our compact subset K. So what we're going to do is we're going to show that this local symplectic cohomology group vanishes for every single disk of finite radius. Okay, so now the fact that these chain complexes were constructed using holomorphic curves inside of our symplectic manifold, you can use this to actually show that this vanishing of this group over the inverse image of a disk of radius A is witnessed by a holomorphic multisection over the disk of radius A. Okay, so we don't get a section quite over the total space over P1, but we get one on every single finite radius disk inside of P1. Okay, so this isn't quite what we want. So there's one additional piece of information or sort of argument that we need. So what we do is a degeneration of the normal Carnot. So we essentially have these holomorphic multisections, and then we degenerate them into our actual desired closed curves inside of P1. So this is a very high level idea. We use Floer theory to get sections over the disk, and then we degenerate them to our actual desired sections inside of P1. Okay, so before I dive in, are there any questions? Yeah.
The inverse image, it might have positive dimension fibres if the inverse image were within that, you've got like neighborhood of multi-section or something, then you look at the complex subset or what?
No. So the compact subset is the inverse image of the disk, and that local symplectic cohomology group will vanish. And when that group vanishes, it's witnessed by the fact that I have some disk upstairs in the inverse image that's wrapping positively around the boundary and essentially just covering the disk downstairs. So that's what I mean by witness. Is that, okay. Why is it holomorphic? Right, so in general, it will be pseudo-homomorphic, and then we'll consider a compactness argument, where we're essentially going to turn off the Hamiltonian perturbation and use some flavor of Gromov compactness to actually recover some holomorphic curves. I'll say something more about this later. Any other questions? Yeah. Yeah. Yes. Yes. No. So it's not technical in that sense. So in general, even when I have like 1 or 0 singular fibers, I don't impose any sort of constraint between the symplectic form and C1. So I use Pardon's virtual techniques, and you don't have to impose anything for that technical reason. I say that it's technical because, as I may discuss, I use C1 to obtain a grading on my Floer chain complexes. No, I really need that it's equal to 0 for this particular argument. I mean, I have some stuff that's in progress where I don't actually think I need the C1 is equal to 0 assumption, but for the sake of this, it essentially comes up because I need a grading in part of my argument, but not because of sort of virtual issues. Any other questions? Okay, so for better or for worse, I'm going in the opposite direction. So I'm going to start with the fact that we can construct these multi-sections over the finite radius disk. And then I'm going to tell you how to degenerate those into your actual desired multi-sections over P1. So once we understand that sort of geometric construction, then I will move on to talking about this local symplectic homology and actually how we construct these disks. Okay, so let's start with the geometry. So we considered the degeneration to the normal cone of one of our singular fibers. Okay, so this is some construction from algebraic geometry. So let's see, I don't know if people online can see the board if I write here. They can? Okay, great. Yeah. So we constructed degeneration of the normal cone in the following manner. So horizontally, we're just going to take some copy of C, and then we're going to take a product with our space M bar. And now lying over the origin inside of C, we have some copy up here of essentially 0 times our singular fiber over infinity. So here I'm kind of drawing a toric picture. And then all we do is we blow up at that singular fiber. So here I will kind of draw this torically, and I'm just going to lop off the corner. Okay, so it's really easy to sort of understand what's geometrically going on in the case where M bar is just P1. Okay, so when M bar is P1, this picture that I drew is actually a perfectly valid toric picture of the ball. So we took C times P1, and we blew up at 0 and infinity. And so geometrically, what's happening in the case where M bar is equal to P1 is just that away from this blow up locus, we have some smooth family of P1s. And as soon as we degenerate to 0, what we get is a copy of the transform of our fiber P1 over 0, and a copy of our exceptional fiber, which I denote by E0. Okay, so all we're doing is we're taking a copy of P1 and we're splitting it off into 2 copies of P1, E0 and F0. Okay, so that's all that's happening in the case where M bar is equal to P1. So again, it's a very similar story when you have this more general family where now you take C times M bar. So again, we get some exceptional locus, but moreover, we also get a map that goes from this blow up, which I guess I'm denoting by P, to this more simple blow up of P1. Okay, so blow ups are functorial. So what's happening away from where we blew up, away from the exceptional locus, we can just identify this particular map pi twiddle between these blowups with our usual map pi that goes from M bar to P1. So we just get this nice identification. And now when we degenerate into the fiber over 0, the story looks a little bit more complicated. So for all intents and purposes, you can just assume that F, up to birational equivalence, is just another copy of M bar. And so if you restrict pi twiddle to F, you just identify the map from M bar, identified with F, to F0, which is P1. Okay, so again, from F to F0, we just get another copy of what looks like our map M. And then we also have a map that takes the exceptional locus to the exceptional locus downstairs. So geometrically, let's see if I had another point there. Yeah, so geometrically, all we're really doing is we are taking our family over P1 and we're splitting it off into 2 families as we degenerate towards 0. So we get one copy that for all intents and purposes just looks like our original family. And then we have some exceptional family that also lives over P1 and it's saying some information about the normal cone. But in general, it's quite singular. Okay, so let me kind of drive home really what's going on the right-hand side of this picture in P1. Okay, so these BZs, these smooth fibers of our degeneration of the normal cone, Gromov converge to this nodal holomorphic curve here, E0 union F0. So as you degenerate these down and towards 0, you get some energy concentration at the south pole, and this forms a bubble that caps off over F0. So here's kind of the very simple observation. If you want to form off this bubble inside of F0, really you didn't need to degenerate all of P1. You could have started with a very, very large disk inside of this BZ. And similarly, when you degenerate it, you get some energy concentration in the south pole. And again, you can bubble off another copy of P1 that'll cover F0. And so this is sort of the key observation. So we can split a copy of P1 into two P1s, but we can also split a disk off into a copy of P1 plus another disk. So let me try to make this more precise in the context of the total space P. So let's suppose that we have holomorphic maps, UZ, that go from the disk to each one of the fibers of our degeneration of the normal. So each one of these PZs. And here we want the image of these disks when we project them downstairs into B to be very large. Okay, so here I just wrote that the radius is 2. So I want them to essentially cover the equator and a little bit more. So to be precise, I want the area of these disks inside of BZ to be larger than the area of the fiber F0. I want to be a little bit precise. So really, you should just think that these are some very, very large disks. And I want to assume that they have uniformly bounded energy. So if we have this setup, then we can construct our desired multi-section. Okay, so this is the lemma that's letting us go from sections over the disk to sections over P1. And so again, the proof is essentially what I previously indicated. So what we do is we take our disks inside of the PZs and we project them down into P1. So we get these disks that cover the equator, or the entire southern hemisphere, and a little bit more. And now we consider the Gromov limit as we move into the zero fiber. So again, because these disks are very large, we get some energy concentration, and it bubbles off a copy of P1. And what happens is now the disk part, or the boundary part of our disk, completely gets pushed into the exceptional divisor, this E0. So we take our disk and we degenerate it now into this copy of P1 plus some other disk here in E0. Okay, so as I stated, the boundary is completely contained away from F0, and we get something that completely covers F0. So now we just apply Gromov compactness upstairs. Okay, so we do the same thing upstairs, and by Gromov compactness, whatever happens upstairs has to converge to whatever is occurring downstairs. So again, it converges to some nodal holomorphic disk. Its boundary is completely contained away from F. But also, we knew that we had a copy of P1 that covered all of F0. So this tells me that there exists a component of this nodal curve that lies inside of F, whose projection down to F0 is non-constant. Okay, but by definition, this is just a multi-section of our map pi when we identify F, the map from F to F0 with M bar to P1. Okay, so this is the sort of idea. So let me make two remarks about this. So the first is that when we consider these particular holomorphic disks, we're not making any assumptions about them having Lagrangian boundary conditions. Okay, so in general, these are just some arbitrary holomorphic disks inside of the space. And so some additional flavor of Gromov compactness is required beyond what you would see in, say, McDuff solid. So I use Fish's target local Gromov compactness to deal with the fact that these are not necessarily Lagrangian boundary conditions. So the next remark that I want to make is, I told you how to produce a multi-section, but okay, there are instances in the theorem where we want actual sections or we want unirulings. And really the idea is still very simple. So if you want to degenerate disks into a section, well, you're going to assume that each one of these disks projects into P1 via a degree 1 map. Similarly, when you run the degeneration, what you get is something that actually degenerates to a genuine section as opposed to just multi-section. And similarly, if you want to get unit ruling, you'll consider disks that have some point constraint that you can take to be anywhere inside of your space. Okay, so you can use this additional information to also get unit rulings inside of M bar as well. Okay, but the essential idea is we take a disk and we split it off into a copy of P1 and some other disk. And all of these additional sort of conditions that we wanted just come along free. Are there any questions about this part? Yeah. Yes. Yes. Sorry.
You have to turn off the homology starting, yes?
Yep.
That's fish argument also working that case with the presence of Hamiltonian.
No. So I turn off the Hamiltonian first, okay. And then I apply Fish's argument. I mean, technically you could, this is what I do. In some sense, you could also apply Fish's this degeneration simultaneously while turning off the Hamiltonian, right? So as you kind of move in towards 0, you take the Hamiltonian to be smaller and smaller and smaller as well. But I break it up into 2 parts. But yeah, So I start with something genuinely whole. Any other questions? Okay. So I will ask a question. So how do we actually construct these disks inside of these fibers of our degeneration of the normal cone? So I already indicated that we wanted to do Floer theory inside of the complement of one of the fibers. So let me fix some notation. So M sub A is going to be the inverse image of the disk of radius A, and M is just going to be the complement of the singular fiber. Okay, so M fibers over C and MA fibers over the disk. Okay, so I said that I want to do Floer theory in M. Now, I want to get holomorphic curves with respect to my integrable almost complex structure. Okay, so if I pick some arbitrary Kähler form that is compatible with that integrable almost complex structure, it does not need to be convex in any sense that is amenable to doing Floer theory. And so this is a problem. So the way that we get around this is via the following deformation trick. So we find some symplectic form, capital omega, on M. And for each one of these fibers of our degeneration of the normal cone, we find an embedding of these spaces into this fixed symplectic manifold M omega. So we take each one of these fibers and we put them in some fixed reference symplectic manifold. And we have two conditions. So the first is that the image of these embeddings lies in this compact subset M sub A. So we take this open thing and we push it into some compact subset. And the second condition is that the end of this M omega is a symplectic mapping cylinder. Okay, so we actually deform it to some very nice sort of end-like structure. Okay, so here's kind of the picture. Naively, you have some wonky looking Kähler form that's not convex, and you take some sort of symplectic completion of this form. And in taking this symplectic completion, this kind of pushes in your original space M into some finite, some compact subset of the completed symplectic manifold. Okay, so I've been using the word convex. So this space is convex, and the sense in which it is convex is that it satisfies an integrated maximum principle with respect to Floer trajectories. Okay, so the end of this is not the symplectization of a contact manifold, but really for all intents and purposes, the Floer theory behaves as if it were just the symplectization of a contact manifold. So the second thing that I want to point out is that this particular end structure has a very nice description in terms of its ray orbits. So if we look at the radial function on our space M, that is, we take M, we project it to C, and we take the radial coordinate in C. Then the orbits associated to this radial function are just going to be covers of the standard orbits of the radial function inside of C. So these are curves that when we project down to C, just wrap positively around the origin for whichever positive integer multiple you want. Okay, so here's kind of the goal that we really want from doing Floer. So we want that for every compatible almost complex structure, we want to find some homomorphic disk in M that covers the disk of radius A, right? So we want to find this multi-section over the disk of radius A for an arbitrary compatible almost complex structure. And moreover, we want the energies of these disks to be uniformly bounded independent of our choice of almost complex structure. Okay, so why is this sort of our goal? Well, using these embeddings psi, we take the fibers of our degeneration of the normal cone, we push them into our fixed reference symplectic manifold, and we similarly push forward the associated integrable almost complex structures. Then we extend them to admissible almost complex structures in M omega. We do Floer theory there, produce our multi-sections, and then pull these multi-sections back along the maps psi. And then we run this previous argument. Okay, so this is sort of a trick that allows us to just work in some nice fixed reference symplectic manifold and actually get holomorphic disks with respect to our desired integrable almost complex structure. Okay, so before I move on to the next part, let me just pause and ask if there are any questions. Right, so yeah, I believe that in terms of getting compactness for Floer moduli spaces, yes, you could get this. However, in part of this argument, I'm going to construct a sort of analog of the action filtration for these manifolds. And in constructing this action filtration, I explicitly use the integrated maximum principle. So from the point of view of defining Floer theory, yeah, I don't think you necessarily need this integrated maximum principle, but for some of the other arguments, it does become necessary. Yeah, any other questions? Okay, let's do Floer theory. Okay, so we're gonna fix R to be our standard radial function. So we project M to C and we just take the norm, the radial coordinate. And we're gonna consider a sequence of Hamiltonians that looks like the following. Okay, so we have H sub n to H sub n plus 1. We have an increasing sequence of Hamiltonians with increasing slope. This is just so we have convexity at the end. And we assume that inside our compact subset, M sub A, that we have a C2 small Morse function. Okay, so really H sub n inside just looks like some C2 small Morse function divided by n. Now the key property that we want this sequence of Hamiltonians to have is the following. So if we have points that are inside our compact subset, we take the value of these Hamiltonians to limit to 0, or really just something constant. And if we're outside of our compact subset, we take the value of our Hamiltonians to go off to infinity. So inside we go to 0, outside we go to infinity. Okay, so we are not working in an exact setting. So we need to work over some flavor of the Nabokov ring to define Floer theory. And the flavor of the Nabokov ring that I'm using is the following. So morally, it's just Taylor series with exponents and positive real numbers. So associated to this universal Nabokov ring, we get a Nabokov filtration that's given by the valuation, right? So morally, just the valuation takes your Taylor series and it associates to it its order of vanishing at the origin. So this is some additional piece of algebra that comes equipped with the Nabokov ring that we will use to define these local symplectic cohomology groups. Okay, so now we kind of do the standard yoga. So for each H sub n, we get a chain complex. So for every one periodic orbit of our Hamiltonian vector field, we just take some copy of the Nabokov ring, and we construct our differential by counting rigid Floer trajectories inside of our space that are connecting pairs of orbits. And again, as usual, we weight by the energy of these Floer trajectories. And we get an analogous formula as well when we define continuation maps among our Hamiltonian Floer chain complexes as well. So in particular, since we required that H sub n plus 1 was strictly larger than H sub n, you can check that this actual continuation map is defined over the Nabokov ring, as opposed to just the Nabokov field. And so we can write down the following slightly cumbersome definition of local symplectic homology for our compact subset M sub A inside of M. Okay, so let's try to unpack this in steps. So we start with our chain complexes, CFH sub n, and then we take the co-limit with respect to our continuation maps. So we have some finite pieces, we take a co-limit and get some infinite complex. Then we take the inverse limit with respect to the valuation. Okay, so all we are doing is we are completing with respect to the valuation of the Nabokov ring. This gives us some new chain complex. Then we take the cohomology of this complex. This gives us now finally a module of the Nabokov ring. And then for the sake of this talk, I'm going to tensor with the Nabokov field. I'm going to kill all finite forms. I'm not going to worry about Nabokov portion. And so this is our definition of the local symplectic homology of this particular compact subset M sub A. Okay, so heuristically, this is some sort of algebraic gadget tree that has the effect of killing orbits that do not lie near your compact subset M sub A. So the way to kind of heuristically see this is to think about this condition that we had on our Hamiltonians, that if we were inside our compact subset, the value of the Hamiltonian went to 0. And if we were outside, the value of the Hamiltonian went off to infinity. Okay, so if we're inside the compact subset, then when we pass to this co-limit, and periodic orbit is going to be identified in the co-limit with other periodic orbits that have relatively small valuation or action, because the value of our Hamiltonian is not changing much. Now, if we're outside of our compact subset, the value of our Hamiltonian is exploding off to infinity. So we're going to identify orbits with orbits of higher and higher action. And so this completion has the effect of algebraically killing these generators that have action that are going off to infinity inside of this co-limit. Okay, and so this is the sense in which this sort of heuristically kills the orbits not near your compact subset. And this is the sense in which this is a local symplectic homology theory. So it's local on the level of generators, but I do want to stress that the holomorphic curves can go anywhere inside of your space. Okay? So it's not like we're just looking at holomorphic curves inside of our compact subset, even though that technically arises in this particular condition that I will talk about today. Okay, are there any questions?
Is there a way to like a symplectic version of ordinary local homology, like a relationship between the definitions?
No, not really.
Why do you not get control of like your homomorphic thing, even though your Hamiltonians are like within a compact set?
Sorry, can you repeat?
So you should. Why do you not get? You said that your homomorphic.
Oh, yeah. So basically, I mean, you'll see it in a little bit. So I use these radial functions, h to the n. And so the orbits are just going to be sitting near the boundary of our compact subset. And so the integrated maximum principle says that they just all lie within the compact subset. Essentially.
You do get that, right?
Yeah, for this very particular case. But in general, M sub A does not need to be the compact subset that you use to define this local symplectic homology group could be a much more arbitrary compact subset. And the definition is sort of analogous. Again, the key sort of condition is that if you're inside the compact subset, let's call it K, the value of your Hamiltonian goes to some constant. And if you're outside of the compact subset, it again goes off to infinity. And you similarly consider the co-limit and the completion with respect to action. Yeah, sorry, maybe I shouldn't have said anything and no one would have noticed. Okay, so what are some general properties of this that we want to use? So the first is kind of standard. Well, this definition was independent of everything that I had to choose. So I chose some Hamiltonians. It didn't depend on these Hamiltonians. I chose some C2 small Morse function. Didn't depend on this. I also implicitly had an almost complex structure that I didn't mention. Again, it also doesn't depend on this. And the arguments are just the usual standard arguments in Floer theory. You just consider continuation maps between your different pairs of data, and these induce the desired equivalences. What is this? What is this? So it's something that's giving some type of categorification of the Hamiltonian dynamics near that particular compact subset.
Maybe it
So
work well to give a simple example, like on some regions of surfaces, on cylinders, stuff like that.
Yeah, so let's see. So maybe the best example to kind of think of this is, unfortunately, a closed example, but nevertheless, let's think about it. So let's take a copy of P1. So here, this equator, this is some non-displaceable Lagrangian. So it can't be displaced by Hamiltonian isotopy. Okay, but now if you look at these disks, these level sets of disks that are just below the equator, each one of these is Hamiltonian displaceable inside of the sphere. You just kind of shift it over. So in general, for each one of these finite disks, this local symplectic cohomology of these disks inside of P1 are actually vanishing. Now, as soon as you hit this Lagrangian, it no longer vanishes. And in fact, you actually just get the quantum cohomology of P1. Yeah. And yeah, I mean, that's kind of the rough idea. So actually,
when you talk about the annuli on a cylinder, I remember something like the local symplectic cohomology was something like the some ring of functions on an analytic space.
So I think the local symplectic cohomology of the cylinder is just the actual symplectic cohomology of the cylinder.
No, like local with respect to some smaller angles.
Right, but
I think a completion of the ring of functions on, C, but maybe I may be wrong.
I think you just get C plus or minus, and you take some completion of this.
I remember something like the completion. It just depends on the size of the annulus. Anyway, it's irrelevant.
Yeah.
Somehow it's mirrored to actual analytic annuli and their width.
I see. Maybe we can talk about this more after. Okay. No, it's fine. Yeah, I could maybe say something else after. So let's kind of get back to this case of P1 that I just erased in some sense. So one of the nice properties or characterizing properties of this local symplectic homology is the stable displaceability result. So if your compact subset is stably displaceable inside of the symplectic manifold, then this local symplectic cohomology actually vanishes. So maybe I'll just briefly recall, a subset is stably displaceable if its product with the circle inside of the product manifold M with the cylinder is actually Hamiltonian displaceable. So if you haven't seen this, when you product with the circle, you can always just slide it up in the annulus. And so you've topologically killed all obstructions to displaceability, and you're just left with sort of the dynamical obstructions. Okay, so heuristically, why does this hold? Well, let's just think about the case where the compact subset is Hamiltonian displaceable. So this says that you have some Hamiltonian whose time one flow takes your compact subset and completely moves it off of itself. So the idea is you use this Hamiltonian to construct this sequence of increasing Hamiltonians H sub n. And this has the effect of creating Hamiltonians that have periodic orbits that are not lying nearby your compact subset. Essentially, because the original Hamiltonian just displaced that subset away from itself. So using this heuristic that this complex kills all the orbits that are lying away from your compact subset, you just get something with null homology. It's very roughly the idea. Now, if you want to get it for stably displaceable, you use a Kuhn theorem. Okay, so the second property that uses the integrated maximum principle is an analogous property that arises with symplectic cohomology of Liouville domains. So you can construct a natural inclusion that goes from the cohomology of M to the local symplectic cohomology of your compact subset inside of it. So if you set SH plus hat to be the cone of this particular map, then you get a long exact sequence that relates the cohomology with this local symplectic cohomology. So I've written this suggestively. So this SH plus is some sort of completed analog of positive symplectic cohomology. That is, you create some complex that's generated by the Rabe orbits that are wrapping around the boundary of M sub A, and then you take some sort of Nabokov completion of it. So one thing where this does not align with what happens with Liouville domains is that this is not an action filtration. Right? So when you construct this long exact sequence for Liouville domains, you say that the critical points of your C2 small Morris function have very small action, and the action of all other orbits is very, very negative, very, very positive, depending on how you like to set up your conventions. And this gives rise to your desired filtration on your Floer chain complex. So in my setting, we're in a non-exact framework. So the action functional is multi-value. So we can't use it to define some sort of action filtration. So the trick is just to use the integrated maximum principle to topologically construct this filtration. Okay, so I said that these H sub n's that we use to define this local symplectic homology were C2 small Morris functions on the interior of M sub A. So there's an obvious map on just the level of generators that takes the critical points of our Morris function to generators of local symplectic homology. The statement is that using the integrated maximum principle, that inclusion on the level of generators is actually an inclusion on the level of chain complexes. Okay. Yeah.
When, because of this displaceability result you mentioned, when the disk is small, but when the disk is large, then you can displace it. Is it still gonna be?
No. Well, what should I say? I don't know. So in the case where the first Chern class vanishes, then it will. And I'll discuss this in just a moment. Yeah. So So let's kind of build on that. So let's think about the case where this local symplectic homology group vanishes. In this case, then we get to the boundary homomorphism that goes from SH plus to the cohomology is actually an isomorphism. Okay, so if we unwind all of the algebra that's involved in writing down this long exact sequence, you see that this isomorphism is witnessed by Floer trajectories that wrap around wave orbits at the positive end and asymptote at their negative ends to the associated critical points that are giving generators for the cohomology. So in particular, we get some Floer trajectory that starts at a wave orbit and hits the unit inside of cohomology. So the unit is represented by an index 0 critical point of our choice of Morse function. Okay, so now we kind of remember some stuff that I already, oh, no, okay, I got mixed up in my slides. So we'll remember that our goal was to produce holomorphic disks over the disk of radius A, and we wanted these holomorphic disks to have energy that's bounded independent of our choice of almost complex structure. So via considering various continuations among different almost complex structures, you can show that the existence and energies of these Floer trajectories that are witnessing this boundary homomorphism in the long exact sequence are independent of all the choices. So they're independent of our choice of index 0 critical point for our Morse function, and they're also independent of our choice of almost complex structure. So as soon as we fix this data, before we fix this data, we have some universal bound on the energy for any choice of data and associated holomorphic Floer trajectory. Okay, so now we kind of see that we almost have what we want. So remember that the wave orbits associated to the radial function on the space M. Yep.
Can you split again the fruit?
Yeah. No, it's fine. Right. So the wave orbits for this particular radial function are just curves that wrap positively around the boundary of our disk of radius A. Okay, so if we think about this, this says this Floer trajectory has one end that's wrapping around the boundary, and now it's sweeping up to fill in the remainder of the disk. Right, so this is giving us a multi-section over the disk, but okay, it's not actually holomorphic, right? So it satisfies the perturbed Cauchy-Riemann equations. So the idea is we want to use a compactness argument to turn off this Hamiltonian perturbation and obtain a genuine holomorphic curve. So let me draw the graphs of the sequence of Hamiltonians that I'm going to consider. So here we have our radial coordinate, and we're going to fix, I think I can do this in yellow, we're going to fix some Hamiltonian at the very end. So we're going to have some fixed radial Hamiltonian at the end, and then we're going to consider the following sequence. So we have, I'll draw this kind of large, we have h sub 0, which is equal to some C2 small Morse function f. And then we have, maybe I'll call this h sub 1. Then we have h sub 2, that's also equal to f now divided by 2. Similarly, we're going to have f sub n, h sub n, etc. So as n goes off to infinity, this uniformly converges to the 0 Hamiltonian that then eventually interpolates into this nice radial Hamiltonian. So we're going to take the Hamiltonian to go to 0 on a compact subset, and we're going to leave the Hamiltonian nice and radial at infinity. Okay, so what we do is associated to this sequence of Hamiltonians, we apply Floer's local compactness. Okay, so we get some sequence of shifts, and these shifts assemble into different pieces of a holomorphic building. Now, in the end of our symplectic manifold, where our Hamiltonian is nice and radial and non-degenerate, our critical orbits are isolated. So our Floer trajectories glue up in this limit. Now, when we are inside, where we took our Hamiltonian to go to 0, now every point is a periodic point of our Hamiltonian. So we don't necessarily have that these spheres glue up together. Okay, but not all hope is lost. So if you look at an interpolating sequence of shifts between any two non-constant spheres, the energy of that interpolating sequence of shifts is converging to 0. So when you appropriately rescale these shifts, these shifted Floer trajectories, you find that they converge to Moore's flow lines. Okay, So the sense in which we have some type of Gromov compactness is that our Floer trajectories converge to Pearl necklaces. That is, holomorphic planes and spheres adjoined by negative gradient trajectories of our associated Morse function that we are taking to go to 0. Okay, so this is how we are kind of getting holomorphic curves. So I have to explain two things. I have to say how we get the multi-sections, and I have to tell you how we get the uniruling conditions. So you'll remember that I said that this was an index 0 critical point. So assuming that I haven't confused myself, an index 0 critical point does not have any negative gradient trajectories exiting out of it. Okay, so actually this tail just doesn't actually happen. And so what we actually get is a sphere and then some chain of gradient trajectories and P1s, and then some copy of a plane that has some part that's wrapping around the boundary of the disk and sweeping inside. And so what we do is we restrict to this particular piece to get our uniruling curves that have our mark point, and we restrict to this particular piece to get our genuine multi-section. Okay, so this is a little coarse. So ideally, you wouldn't like to actually have these trajectories rise, and you'd say that really you could get some uniruling by sections or multi-sections. But in general, these split off, and this is how we get these two individual pieces.
So uniruling curves are, those are basically the curves on the total space.
Yes.
But they're not living on fibers, right? I'm just asking a basic question. So they are not necessarily living in fibers.
So technically these could. Yeah, so technically when you run this degeneration, you could have that your Floer trajectory bubbles off this index, sort of part of your cylinder into one of the fibers.
But do you actually construct a family there, family of P1s there?
Do I actually construct the family of?
For uniruling the total space.
Right, so this is an index 0 critical point. So I can pick any choice of Morse function that has an index 0 critical point at any point inside of my domain. So for every choice of these Morse functions, I get one particular P1 passing through my desired point.
Okay. And you don't have to construct a family. You just, it's enough, I don't know, maybe it's okay if you know that.
Yeah, if you just know that you have one through every single point. Yes. Are there any other questions? Okay, so what's the upshot of this? So if local symplectic cohomology vanishes, then we essentially get a disconnected curve with boundary, such that one piece is giving us a point constraint or a uniruling, and the other piece is giving us our desired holomorphic multi-section over the disk. So the final thing I need to tell you is why local symplectic cohomology vanishes. And in this case, then you'll be happy. You'll know how to get your disks. Okay. No, that's fine.
So you construct you construct this holomorphic plane under the assumption that the symplectic cohomology vanishes.
Yes.
And that's because can you tell me just very briefly again why that was the case? Like, why don't you have, for instance, this sum of?
Why don't you have some of?
Like this cohomological vanishing tells you existence of a single chimera.
So if there were no curves,
okay,
then your differential would be 0. Or the boundary homomorphism would be 0. So the fact that you have some actual isomorphism, or that this curve is an isomorphism, says there exists at least one holomorphic curve that's witnessing this count.
So you are actually killing the boundary of the disk.
And the boundary of the disk is killing the point class, if that makes sense.
Okay. I missed some stuff here, but I may interrupt more with.
No, it's fine. Any other questions? Sorry, repeat that?
If you interpret this result by some kind of non-vanishing condition for open merit, one constraint.
Yeah, so that's
And then in that case, maybe in a case with the presence of two singular fibers, you can apply federation to normal form and have two pieces. Each individual piece has only one singular fiber. And you can somehow argue that their most invariants are now vanished. You like sometimes argue the Louis argument to upward result for single fiber.
Yeah, so that's an idea. I mean, in general, I just see these Floer trajectories and these particular annular disks. So I'm really just sort of gluing them up or kind of filling them in over one end and not necessarily over the other end. And so I would need to find some way to keep stretching these disks further and further out towards infinity. And this kind of becomes this becomes an issue.
I think there is a result of Floer saying that
yes, but I haven't. Yes, I'm just saying that the current setup that I have in this argument, I don't see an easy way to pick off the Gromov-Witten count, or sorry, get that particular Gromov-Witten invariant here. Yeah. Any other questions? Oops, there we go. Okay, so let me try to explain this. So we have two cases corresponding to the two cases in the theorem. So one, we have no singular fiber over 0, or we have one singular fiber over 0. And in the case where we have one singular fiber, we assume that this term class vanishes, and we want the vanishing of local symplectic homology. So let me briefly dispatch of the case where we have no singular fiber over 0. So in the case where we have no singular fiber over 0, then actually this is a submersion over C. So diffeomorphically, M can just be written as a fiber times a copy of C. Okay, so the statement is that actually you can realize this after symplectic deformation as an actual symplectic product. So you can actually arrange for this space M along with the symplectic form that I read omega to just be the product symplectic form on the fiber and the copy of C. Okay, now in C, every compact subset is Hamiltonian displaceable just by take the real coordinate. Okay, so now you just pull this back to a Hamiltonian on M. And this has the effect of making every compact subset inside of M be Hamiltonian displaceable. So in particular, the inverse image of the disk of radius A is Hamiltonian displaceable. And so we can appeal to this result of Mark and Umet to say that this local symplectic cohomology vanishes. Okay, so for the case of right, so this is what I will state now. Yeah. So what do we do when we have a singular fiber? So we have some type of singular fiber, and we have a whole bunch of smooth fibers. So the first thing we do is we appeal to results of Mark and Klein. So an H principle states that this fiber, being a positive codimension subvariety of a Kähler manifold, is stably displaceable inside of this manifold. Okay, so in particular, we can find some very, very small disk about this singular fiber that is stably displaceable inside of the space. Now, the rub is that M epsilon is probably going to be much, much smaller than our actual desired compact subset M sub A. And we really want vanishing for M sub A. So the idea is to construct a rescaling, right? So the disk of radius epsilon looks a lot like the disk of radius A. You can just rescale by epsilon out to A, and similarly, you can rescale your Hamiltonians outwards as well. And this is very roughly speaking the idea. You essentially construct some sort of rescaling of your Floer data from M sub A to M sub epsilon or vice versa, and you study the associative map on the Floer chain complexes. In general, this does not behave well with respect to completions, right? So the completion is something that really saw the action, and the action is getting picked up by the areas of holomorphic curves or your Floer trajectories. And unfortunately, an epsilon disk does look different than a disk of radius A. And so this presents some issues. And so to circumvent this, you use the grading of C1 being equal to 0. But I think I've probably gone over time. I don't actually remember when we started.
I would say like another 5 minutes.
Okay.
By the way, can't you do Meyer-Vietnam's property? Just do the disks that use local vanishing result?
No. You can, but essentially the issue is that you look in C and then you look at this annulus. And the local symplectic homology of this annulus is not necessarily the same as this annulus. And so Meyer-Vietoris tells you that yes, this local symplectic homology of M sub A for A very large is just going to be whatever this first non-trivial annulus is. Now I suspect that it's 0, but at this point I can't prove that.
You don't have to cover by annuli, right? You can cover by small distance.
Oh, but if you cover by small, so to apply, so maybe I'll say some things for the maybe slightly less informed. So these local symplectic homology groups via the work of Umet-Verognes satisfy a sort of Meyer-Vietoris property. So if you have a covering of your space by compact subsets, you get some Meyer-Vietoris sequence associated to these local symplectic homology groups. However, you have to impose some sort of constraints on the intersections of these compact subsets. Namely, you need some co-isotropic assumption for where these intersect. And so in general, if you just take some small balls, this condition gets broken. Right, in fact, if you could always do it for small balls, you would say that the local symplectic homology of every space would always vanish, and eventually you get quantum homology, which is not 0. Yes, but when you do these annuli, then in this case, the overlapping boundaries are perfectly fine for Umet's construction. Yeah. Okay, so maybe I'll try to do this quickly, at least enough to indicate what the problem is and why you need C1 is equal to 0. Okay, so we rescale. So phi takes the disk of radius epsilon out to the disk of radius A. And so we fix some sequence of Hamiltonians that are going to compute this local symplectic homology for M sub epsilon. Then we also construct an analogous sequence of Hamiltonians, Hn twiddle, and we assume that phi relates their Hamiltonian vector fields. So phi takes the Hamiltonian vector field for the disk of radius epsilon, and it pushes it forward to the Hamiltonian vector field for the disk of radius A. Okay, so because we get this identification of vector fields, we get an identification of their Floer chain complexes. However, to make this an actual isomorphism of chain complexes, we need to account for the fact that holomorphic curves have different areas. And so to do this, we need this weight. So we take some orbit, we map it to its associated orbit, but then we rescale it in the Nabokov by the Nabokov parameter of a rescaling amount times the amount that that orbit winds around C. Okay, so in general, this is not a bounded map. Bounded in the sense with respect to the valuation. Right? In general, as the radial Hamiltonian increases in its slope, we get orbits that are now wrapping more and more and more times. Okay, so because this is not a bounded map, it will not induce an actual isomorphism of the completed complexes. And essentially the simplest example to sort of see where this fails is again this case of P1, as you push out from the South Pole towards the equator. You can similarly construct a rescaling and you can very explicitly see where this fails. Okay, so the idea is to use C1 is equal to 0 to get a grading by Conley-Zender indices on the Floer chain complexes, and instead show that this map is degree-wise bounded, which is to say that for any fixed Conley-Zender index, we only see periodic orbits that have some bounded winding number. Okay, and so the way that we do this is essentially by working with some very nice construction of Hamiltonians that are adapted to a normal crossings resolution of this particular singular fiber. Okay, but once we get degree-wise bounded, this is enough to give us the rescaling isomorphism. Okay, so that's all that I had. So I appreciate your time.
Thank you.
The second knowledge have a repeat logical structure. So we should have a big here.
Yeah.
In a defined case, there's something called a degeneration.
Yes.
Yeah. So you can use that to continue with.
Yes.
Okay.
Yeah. So I'm not super familiar with this, but so let's see. So you look at the S1 equivariant.
Oh, still all the
What?
Still all the
Yes. Right, and this is essentially that the identity is getting killed on some page of the spectral sequence for S1 equivariant symplectic homology. Yeah, you could similarly do that, but I think you're going to run into the exact same sort of issue. I think that at some point, you know, for a disk very, very small, you'll see that on some page of the spectral sequence, you kill it, but then you do this rescaling and you see how the pages of the spectral sequence changes. And you don't necessarily, you know, get an isomorphism of the pages of the spectral sequence. Yeah, sure. Yeah, I think the analogous construction should absolutely hold that.
Yeah. Only with comment about the size of the analysis, etc. that I made about conflict now.
Okay. Yeah, I mean, actually, by omits. Essentially by omit sheaf property, once you have some fixed annulus and you know what this particular group is, you just take a copy of it and you shift it over and you just, yeah. So in general, very small annulus is the same as a very large annulus. Yeah. And essentially what's going on is that, okay, the reason why you can expand here, but you couldn't expand in C, is that here, okay, you could look at Conley-Zender index, but you also have another very natural topological rating. It's given by the winding numbers. So in this case, winding is a filtration. In this case, winding is an honest to God rating. And so here you could rephrase everything without knowing what a Conley-Zender index is. Get that this rescaling is an isomorphism as well.